point or focusing type of collector. Here what we can see is the sun, the radiation from the sun will fall on the collector, which will be concentrating on the absorber, and the absorber or a receiver which takes the solar radiation is of a very small area. In the previous discussion we have told, or we have discussed about conical or cylindrical type of collector, that is nothing but a line focusing collector or cylindrical type of collector. But this is a kind of parabolic collector, or we can say it is a paraboloidal because it is a three-dimensional, and it focuses at a single point, unlike previous discussion on line type of, this is point type. So the temperatures what is raised is very high compared to the line focusing collector, because in the line focusing collector the concentration of radiation will be along the line, but the same intensity, if it is focused at one point, we can see very high temperature rise. So in that case we can see very good temperature rise, and we can extract more energy from the solar radiation. And point type of focusing collector will have high concentration ratios. Concentration ratio is the ratio of the area of the concentrator to the absorbing area of the receiver. So it is the ratio of this one area, collector area, what you can see in the video, the pointer area, to the absorber area. So this is receiver, absorber, or we can say engine, or anything which utilizes the energy. There can be many forms which extract the energy, but we can have very good concentration ratios. So in the picture we can see the solar radiations that falls on the collector of a very large area. Nearly the diameter would go up to 6 meters, or maybe higher than this, but it's a general configuration. So for 6 meter dia collector, there will be somewhere 200 small mirror segments that actually reflects or focus the light at the receiver end. And the feature of this type of collector is it has two axis rotation in the sense it can move up and down, and also it can turn right and left. So one axis horizontal, one axis vertical, so there will be two axis rotation is possible. And as I have told, there will be high concentration ratios up to 100. So this is very important. Concentration ratio is nothing but you take the ratio of the larger area to the smaller area of the collector. So larger area is always collector and smaller area is always absorber, which stores the radiation energy which comes into it in the form of liquid collection, or it may be a PV cell, or it may be an engine, anything. It absorbs the energy. And the temperature rise could go up to 300 to 500 degree centigrade. So this is a quite high temperature where we can expect good quality of steam coming out of the concentrator to generate power. So we can directly supply this to turbine, the steam, if it is at 500 degrees centigrade. So this is a quite high energy concentration type of collector, and there are some disadvantages also. Because it is a point focusing collector, tracking should be very precise, and it won't consider any diffused radiation, very less actually. It only focuses with the beam radiation, it works with the beam radiation. And also you know that it has a 2 axis rotation freedom. That means it has to precisely track the sun along the 2 axis. Actually it varies, the sun position varies in both the axes, so it is important to have a tracking system, good tracking system, which actually increases the expense and maintenance cost. Next we have sub classification of this point focusing collector, that is distributed heliostat reflector. This is also a point focusing collector. In this, what actually happens is, unlike a whole setup focusing or tracking the sun, here the absorber and the reflector are separated. So the whole reflectors are placed on the ground. There will be central tower. So there will be central tower, and this central tower is having the absorber here. So these are collectors, the whole area is collectors, and this is only the central tower is absorber. So what it does is, the radiation from the sun falls on independently rotated or independently reflected mirrors. These mirrors are called heliostats. So these independent mirrors, they are called heliostats, and these mirrors focus the light to the top of this central tower. So the top of the central tower has receiving end, so it absorbs the radiation. The top of the central tower absorbs the radiation, and it will be used for power generation. But the problem associated with this type of system is, each independent mirrors should be positioned separately. So again, the mechanism of tracking the sun is non-linear with respect to each mirror, so it becomes little complex to focus the sunlight from all the mirrors to one tower and one small location at such a long distance. But this is achieved, and there are some setups which actually run on this type of systems in California. And the mirrors arrangement is called, this type of mirrors arrangement is called dilute mirroring. Dilute mirror in the sense, we can see there is a small gap between each mirror. This small gap, what we can see here, this small gap here between each mirror takes over 40% of the total area. That means if you are placing 10 mirrors here, that actually makes you to use only 60% of the space. So remaining 40% you have to allow it for as a surrounding space for rotation. This has a problem. So your collection area is only 60% of the total area. This type of mirroring is called dilute mirroring. That is one energy loss what we can see. So compared, if you have a complete solar panel over this place, that would have used all the 40% of the space, and 100% area is utilized for power generation. That is not possible in case of distributed heliostat reflector. In this slide, what we can see is a concentrating type of flat plate collector, but these are non-focusing type of collector. In the sense, the in this the radiation energy which is falling from the sun to the collector will get reflected to the absorber, and the absorber is a flat plate. The light radiations are only reflected, they were not focused at a single point, so it gets reflected all over the absorber plate. So there are two designs. One is a simple design, flat plate collector with augmented mirrors. So this is the flat plate collector. The bottom one, what we can see is an absorber, and these two side things are left mirror and the other one is right mirror. When solar radiation falls on it, they will reflect the light towards the absorber. So by this we can get extra lighting that falls on the absorber plate, and because of this we can extract beam radiation as well as some part of the diffused radiation. And this is a simple mechanism, but still the angles of the mirrors should be monitored such a way that it reflects the solar radiation to the absorber. Along with direct light, the absorber will also get the reflected light. So this is concentrating type of light. So here light is concentrated, but the radiations are not focused in any single point, so it will be directly absorbed all over the surface of the non-focusing type of collector. And in the picture here, that is compound parabolic concentrating collector on the left, what we see is parabolic concentrator. Instead of having the flat reflecting mirrors, there are parabolic reflectors, and these parabolic reflectors will also help to extract more solar radiation. And one benefit is when sun turns from east to west, without tracking system, this type of reflection can extract more energy than only a normal flat plate collector. So instead of having a tracking system to focus the light, so we have a parabolic concentrating type of reflectors on the both the sides of the flat plate collector. So this is a flat plate collector, and these are the parabolic concentrators, and there are some other simple concentrator, and there is a solar cell which actually absorbs the radiation. These are, that is called absorber plate, and we have a circuit which actually extract the radiation from this semiconductor material. So this is one type of compound parabolic collector. So this is non-focusing type, and there are some of the advantages. That is, one is it don't need any tracking system, and it absorbs diffused radiation along with the beam radiation, and the ratio of concentration is very high, and in this system the temperature rise can go up to 150 and 200 degrees centigrade, and the concentration ratios can go up to 10,000. So to conclude, there are few advantages like a tracking system, high concentration, but these are not a focusing type of solar collectors. Hello everyone, welcome to video lecture on solar energy storage systems. Solar energy is an abundant source of energy to the earth. It is also a renewable source of energy, and we know that many forms of energy what we get on earth, rain, wind, biomass, everything, agricultural things, everything, the main source is the solar energy. And the problem with the solar energy is We don't get it continuously and with the uniform intensity to the earth. The energy is intermittent, and the energy is also uh, having not much strength. I mean to say, one point of the time the energy is high, and one point of the time the energy intensity is low. And it is seasonal also. During rainy season, during during summer, it is very good, and due to its rotation about itself, morning, evening, afternoon, then during nights, then during cloudy time, dust, dirt on the collector. So many factors affect the uh, energy extraction from the sun. We can say, though it is renewable, and it is main source of energy, we cannot completely depend only on it because of this drawback what I have discussed. So we need some storage system to store the energy, because we can use it whenever it is available, and whenever the demand comes to the energy. And we need to know what are the steps that are being taken to store the energy. What are the methods that are available to store solar energy? Solar energy comes in the form of radiation energy, and radiation energy can be stored after converting into other forms of energy. In this slide, we see what is the need for storage of solar energy. The main advantages of storing the energy is we can store the energy whenever the available uh, energy is excess, or we can say during summertime or during sunny days when there is a bright sun. We can store the energy from the solar radiation, and we can use it when there is a less brightness of the sun. Example, during night time, we can use that same energy what is stored in the morning time. That is, we can absorb the more radiation when it is available. And it is easy to respond to the varying load, in the sense, all of a sudden if cloud comes and obstruct the sunlight, at that time the load remains same. So if load is same, and there is no radiation coming into the generator, power generator, then there will be problem. That's why we need to supply more power when the load demand is high, and input supply, if all of a sudden goes down, then we can supply the stored energy and we can maintain the grid power. Then we can improve the reliability of the solar energy. So if we make the storage system, we can improve the reliability on the solar energy. So there are two types: there is solar thermal and electric power. So if we store energy in the form of thermal energy in the daytime, parallelly if we use electric power during morning daytime, that night time solar thermal energy can be used to produce electric power. Because for example, PV cell, if we take, PV cell can produce power in the daytime, which can be directly supplied to the grid. We can supply that to the load, or to the houses, or to the factories, whatever may be the application. So that for that we can directly supply to the grid. Then if we need to supply the power during night time, then PV cell, photovoltaic cell will not work. And in that case, in that sense, if we have stored the thermal energy in the different means like water heaters, solar water heaters, or in the form of solar pond, if we store that energy, then during night time we can use that power. So these are some of the needs of storing the solar energy. So alternate systems can be used. To conclude, we can say it is important to store energy, as sunlight is unreliable. We cannot get constant power. Then what are the methods available for storing the solar energy? So we can see thermal energy storage technique, electrical energy storage technique, chemical energy storage technique, and mechanical energy storage technique, and we have electromagnetic storage. Here the thermal energy storage, in the sense solar water heaters, directly radiation is converted into heat stored as low grade energy in solar ponds and in solar water heaters, and some other thermal energy storage applications. If it is electrical, we can store it as capacitors. So electrical capacitors will also store electrical energy, and we have batteries also will store the electrical energy, and we have chemical energy storage. There are some chemicals which will store the electrical energy in the converted form. Then mechanical energy forms, like you can pump the water into higher positions. Then during night time you can use that water and generate the power. So during daytime we will store the water at elevated tanks. Night time we will release that water into the turbines and we will extract the power. There are some other options, like we can store mechanical energy in the form of flywheel. We can store even flywheel also stores compressed air. So if we compress the air, that also stores the energy in the form of mechanical power. Then it is released to run the turbines. Then electromagnetic storage, using some superconductors to store the energy. The solar energy is stored. These are some of the techniques that we can see to store the energy, but not all these techniques are popular because they have some constraints. Here in this slide we can see SlrPond. SlrPond is one of the easiest device which actually extracts solar radiation energy and stores in it. Very simple, and it is cheaper option of storing the solar energy. So what is a solar pond? Solar pond is a pool of salt water which collects and stores solar thermal energy. So you can note down, solar pond is a pool of salt water. So I have taken one picture from the internet source. You can see here this whole thing is a solar pond, and it has salt water in it, and it collects the solar thermal radiation and stores it inside this, which will be used for the power generation later. After extracting the heat, that will be used to run the turbines and generate the electrical energy. So this is how a solar pond is seen. We'll study in depth about this topic. This pond has water up to some depth of some, say, 5 to 6 meter depth water tank. In this tank the water absorbs the solar radiation, but if you can remember the effect of convective heat losses in the sense, if there is a object, and if it is hot, say at some temperature 30 degree, and atmosphere temperature say at 20 degree, when this hot body comes in contact with this cold body, the heat is released to the cold body. So that is why that type of system loses heat always as a convective heat. That's why here, if we have only water in this pond, and at the bottom, if there is a black surface which absorbs solar radiation, thus it releases its heat to the water. So water gets heated up at the bottom. So you can see here in this picture, solar radiation, sun is here, the rays comes through the different zones and it enters and it reaches the black surface. So the bottom surface is black. So this black surface, when absorbs solar radiation, it heats the water exactly on its top surface, exactly the first layer here, in this portion. It absorbs the solar radiation coming in this direction, the solar radiation, and it absorbs and heats up the bottommost layer. But because there is a convection principle where the hot water slowly goes up and settles on the top, being lighter, and the cold being dense, it comes and settles in the bottom. So if we take a cup, so always we can see hot water on the top and cold water in the bottom. So even if you heat, if this becomes hotter, it will move up like that. So this type of system will not allow the solar energy to be stored in this system, because as soon it gets heated up, the water will move up, and that air continuously takes the heat away. So what is the end point? So we don't get any heat stored in the water. So that's why what we do is, instead of allowing this water packet come up because of the high temperature, we have to stop this somewhere here. This heat, whatever the heat it gets, should not be allowed to move up as a convective heat loss. So once this moves up, the air easily takes away this heat. So this system is called convective heat loss, and to avoid this convective heat loss, what is done is we have to add the salt to the water. So once salt is added to the water, the water density increases because of addition of salt. The density of water when gets increased, it will try to retain the water content in the bottom zone. So to say, the denser fluid will always stay at the bottom level, and lighter fluid always stays at the top level. That's why the addition of salt will help us to store the solar energy. Actual process we will discuss with respect to this picture now. Looking at this picture, we can say that the solar pond will have 3 different zones, which we can see from the picture, and I will also show the next slide the same thing. So there will be 3 different layers. One is upper layer, the second one is non-convective middle layer, and the third one is storage zone. That's what here we can see. First one is upper layer. This first one is upper layer. This is called upper convective zone. Usually it will be below 5% of the total depth of the tank. This will be usually below 5% of the total depth of the tank. Next, we have the middle non-convective zone. This is middle non-convective zone, which accounts for more than 50% of the thickness of the solar pond or depth of the solar pond. So this is quite deep compared to the upper convective zone. And the third one what we have is lower convective zone. This is lower convective zone. So this part is lower convective zone. Here this is, you can see this is convective zone, this is convective zone, and this is non-convective zone. Again this is convective zone. In this system what actually happens is the radiation from the sun passes all the way through this different zone, and as I told, it heats up the bottom surface. That heat will be stored in the salt water, and this salt concentration is such that it will be super saturated. So you should remember that this lower convective zone is super saturated salt water. Super saturated salt water means there is no option that putting extra salt into that water will dissolve in it. So it won't take any small quantity of water. So this is super saturated, so highly dense. Because this is dense, and the upper layers are fresh water. So these are fresh water. That means the concentration of salt is very less. So somewhere around 5% or 6% will be there, the concentration of salt in this region. That means fresh water. So this is fresh water being lighter, because there is less salt concentration, it is lighter and it floats in this solar pond. So upper surface is convective region, and it is cooler because this is away from this heating surface, and there is no convection taking place from the lower zone to the upper zone. So this is blocked because of the central layer. This central layer is non-convective zone. This will be a barrier kind of thing for the convective heat loss. And because of gradient in salt concentration, say from upper to lower, slowly the concentration of salt will vary. So if you see this graph, from this coordinate system along the x, if we take the concentration, if we take along the x-axis, so the concentration is high at the bottom layer and concentration is low at the top surface. So this is the curve, how it varies. And in the non-convective zone, gradually the concentration changes. So that means from this end there will be high salt content, and at this end there will be less salt content, and here it is uniform throughout. And this, any small temperature rise here will be lost to the atmosphere as a evaporative losses, and also some part of the heat is lost as a reflected light, and the incident radiation which efficiently reaches the bottom gets converted into heat. So that can be seen here also in this picture. And roughly the useful heat is extracted at temperatures somewhere near 90 degree. So the temperature ranging from 90 degree centigrade can be seen at the bottom layer, and this is varying salt concentration. That's why this water will remain here itself, being dense, it won't go up, and the heat loss to the atmosphere from this is blocked. and care should be taken such that there won't be any turbulence or any molecular diffusion that takes place in this pond, so that will reduce the performance of the solar pond. Next, we will see how solar pond will allow us to get the electrical energy, how we extract the energy from the solar pond. So anyway, we know there is a hot water here at the bottom, and this hot water will be taken to the evaporator. This part is evaporator. So this part is evaporator. What it does is, it takes the hot water from the pond and it vaporizes the working fluid into steam that enters the turbine. That temperature hot water which flows through this pipe will gets cooled because it loses heat to the working fluid. There will be a working fluid like some Rankine cycle, or we can say some organic fluid, some ammonia or some refrigerant kind of thing. If we use low boiling point fluid, which will gets converted into vapors easily, and that will be made to flow through the turbine. So this turbine rotates and it generates the electricity, and the remaining part of that steam is to be converted into back to liquid. That is done in the condenser. So the condenser will take the cold fluid either from the top surface, or it can be from air, atmospheric air. So even some condenser is sometimes condenser is replaced by cooling towers. So even cooling towers will also do the job. Only thing is, it should take the heat away and condense the steam which comes into this condenser, and that will be released to the solar pond. Otherwise, the working fluid is in closed loop, it will be pumped back to the evaporator. The liquid is pumped back to the evaporator and it gets converted into steam. So I will repeat. The fluid, hot water, is extracted to evaporator. It releases its heat to the working fluid and comes back to the same place. Then let us say the working fluid is coming and it takes the heat released by the hot water, and the working fluid becomes vapor or steam. It enters the turbine. Then after releasing its energy, it has to become liquid again, so it will go to the condenser where it becomes liquid and slowly comes back to the evaporator, and the heat is absorbed by the condenser, and that heat will be either released to the atmosphere, or the surface of the water is heated so that further convection can be avoided, because there is a high temperature which air only takes care of taking the heat away from this surface convective region, so the cold water can be used again and again. So this is how the energy from the hot water is extracted. There is a problem in this, that is, during taking the fluid hot water from this bottom surface to this evaporator, there should be care taken to avoid turbulence. Turbulence in the sense, it mixes water of different layers because of its turbulence motion. The convective layers will get affected, three zones will get affected, and the heat will be lost. So there won't be much fluctuation in the fluid level, or there won't be much bulk motion of the molecules in this region. So to avoid this bulk motion, the flow is made or maintained in a laminar way, so it will not disturb the top layers. So smooth laminar flow should be maintained. For a brief idea, the energy extraction can be as this much. If we say some 2 kilometer surface area is made to extract the solar energy, if the pond size is 2 kilometers area, then we will get power of only 20 kilowatt. 20 kilowatt is a small power compared to the size what the pond is. So it takes very large power, but the cost of this system is very less. There is only water and a black surface, and a little salt can give the sufficient power. So the investment is very less. Only thing is it requires more space, and the conversion is very less. Only 20 kilowatt of power we will get with the solar pond of 2 kilometers size, that is constructed in Australia. So there is a plant based on this capacity. And some of the drawbacks we can discuss. So if you see in this picture, the challenges faced by the solar pond are: one is dust. So if it is open to atmosphere and it is there in some field like this, any leaves or whatever the dirt, agricultural waste, or some material, garbage or anything can come and fall on this tank surface, and that will cover the surface gradually. So every day this is to be cleaned, like how swimming pools and all will be maintained. Like that, the dirt on the surface will affect the collection of solar light in the solar pond, and silt deposits down. If it is a dense material like sand, dirt, but that is being carried by the air or winds, that will also affect the absorption of solar light from the black bottom surface. And if it is wind, and if there is rain, that will create turbulence or waves in the pond. So this will affect the different layers. So if rain comes, these different layers will get affected. So the rain or wind, if it makes the wavy motion of the water, then we cannot maintain this type of three different layers in the pond. So these are some of the disadvantages. And the salt, whatever is used in the solar pond, should have the following characteristics. It should be a good soluble in water, and the solubility of this salt in water should not vary with respect to temperature. In the sense, the salt concentration should not change with respect to the temperature, and solution should be transparent. It should not have any color. Normal salt will be transparent, but if there is some salt based on minerals like potassium and all, there may be color change, like reddish salts are available, and some salts have some colors, so that should not affect the performance of the solar pond. So there should not be any color, it should be transparent. And the salt should be environmental friendly, so the salt should be environmental friendly, and also it should be of low cost and available easily in the nearby place. So these are some of the characteristics of the salt, challenges that are faced in the solar pond. In the solar pond.